Hello everyone and welcome to another session on general microbiology where we are going to be learning about the staining techniques, right? So we've already covered the morphology of bacteria, so now we want to see how we can stain the different bacteria. So the first thing that we're going to start with is that why do we even need staining, right? So why do we need staining? Because we cannot see bacteria because bacteria are translucent. Right, so that is why we need the stains because bacteria are translucent, and if we want to see them under the microscope, they will not be very much visible. Seeing this picture on here, so can you see this is an unstained picture, and when I have stained this, how the contrast has increased. So all the pictures on the left are the unstained ones, and as soon as I have stained them, how much more properly they are visible. Right, so that is why it is important to stain because we want to see the structures properly so that they can be properly seen under the microscope. So because bacteria are translucent and to see them under microscope, right? So as we said, staining leads to what? Staining will lead to increase in the contrast and make the bacteria more visible. So whenever we do the staining, the first thing that we do is that we prepare a smear, right? So we take the colony and then we prepare a smear on a slide. So smearing is nothing but taking a colony and making a round colored thing. So after we have made the colony, so we can make smears either from directly the samples, or we have, if we have isolated an organism and we want to identify it, then we can take it from the colony that we have grown on the culture. So that is the way two types of smears that we can make, either directly from the specimen, the clinical sample, and the other one is that if we have isolated a colony on an artificial media, we can make the smear from that. So on a glass slide, we make that smear, and then what do? We have to fix the specimen. So we have to fix the specimen. What will the fixing do? What will the fixing do? It will basically attach, or it will kind of fix the organism on the slide, and it will also lead to what? Fixing of the internal structures. So because we want to see the internal structures, can you see here also we are seeing so many internal structures. So because we want to see the internal, we want to keep those internal structures intact. Right, we don't want them to disseminate when we are staining them, so we want to keep the internal structures intact. That is why we have to fix the specimen. So we have to fix the specimen to keep internal structures intact, right? So how do we fix? So we can fix it by two methods. Either we can do the heating, or we can do some kind of a chemical method. So heating may, what do? The smear that we have made on the slide, we can do it flame heating. That means that flame that is there of a candle or whatever, we just run the slide on it 2-3 times, and that is what is known as flaming. Second thing is air drying. So that we under the fan only, we are leaving the slide for it to be air dried. So that is known as your air drying. But the disadvantage to this is that whenever we are heating the samples, we are flaming the samples like this, sometimes what can happen? The internal structures can get charred, they can get disrupted. So the disadvantage here is that the internal structures can get disintegrated. Right, so that is one of the disadvantages of your heating. That is why we came up with another method of fixing the sample, and that is your chemical method. So what chemicals can we use? We can use the glutaraldehyde, right? We can use the glutaraldehyde that we used for the electron microscopy. We can use the acetic acid. We can even use mercury chloride. So what are the advantages of these? The advantages are obviously that the internal structures will be preserved, like they will not be disintegrated, the internal structures will be preserved, and even we can use this for fixing the blood smears. So even used for fixing the blood smears, right? So these are the advantages. So these are the advantages. Got it? Okay. Coming to what are the common stains that we have. So we have certain common stains. The first one that we're going to be talking about is your simple stain. So simple stain are what? They are basic dyes that stains all structures equally. So they are simple stains. They don't differentiate between anyone. They will stain everybody the same. So can you see here? It doesn't matter the morphology, it doesn't matter the cell wall, it doesn't matter to the simple stains, anything. They are saying that we are basic dyes and then we are basic people, we are going to stain everybody equally, right? So they are the simple basic people. So what are the examples going to be? It's going to be methylene blue, right? Methylene blue or basic fusion. So these are the basic or simple dyes that will stain everything equally. So this is the methylene blue and how they have stained all the structures as blue. Coming to the next one, which is called as your negative staining. So negative staining, whenever we talk about anything negative, that means we are trying to stain the background. So we stain so background is stained here. So the structure is not stained, but the background is stained. And what happens because of the staining of the background, the organism becomes visible, right? The organism becomes visible. Where can we use this negative staining? We can use it for two things, for the capsulated organism, either for the capsulated organism to see the capsule, or for those organisms that are so thin that they cannot take up the stain. Right? They are so thin that they cannot take up the stain. And what are those? They are the spirochetes. So spirochetes, which includes your syphilis, your borrelia, and your leptospira. So they are actually poorly stained. So that is why we can use this kind of a stain, which is known as your negative staining. So it will stain the background and the organism will become visible. So let's see here. Can you see this picture? Can you see this structure? What is happening? This is the organism and this is the capsule of the organism. So here also the background is dark. And can you see this structure? So this is the spirochetes. So this is the spirochetes. So what all stain can we use? What are the examples of stains? So there are two stains mainly. One is your India ink. One is your India ink and the other one is your Nigrosin stain. So these are the two stains that you can use for your negative staining, right? Coming to the third one, which is your impregnation. So impregnation, as the name only suggested, we are impregnating something on something. And what is that something and something? So we are taking a stain and impregnating it on structures on the bacteria that are very, very thin. Either the whole bacteria or just a structure on the bacteria. So let's look at this picture. What is happening in this picture is, so this was a bacteria which was almost not visible. Then what we did it, we kind of impregnated something on this, then kept impregnating it to the point that it started becoming visible. It started becoming visible. And what do? We use a stain here, which is known as the silver impregnation stain. So what it does is the silver impregnation stain, it will go and attach to the bacteria, either whole of the bacteria or some structure of the bacteria, and will keep making it thicker, thicker, thicker till it becomes visible, right? So what can it show? It can either be used for very thin bacteria, like what? Like again, your spirochetes, or very thin structures of the bacteria, like what? Flagella, like your flagella. So it can either be used for flagellar detection or even for your very thin bacteria like your spirochetes, right? Then coming to the differential stain. So what does differential stain means? Differential stain means that this stain is particularly used either to differentiate between two bacteria who are different, or the same bacteria which takes stain, say like two structures of the same bacteria stained differently, right? I'll repeat it again. Differential stain means that either you are differentiating by the help of a stain between two bacteria, or you are in the same bacteria staining two separate structures differently. I will explain it once we see what all stain comes here, right? So stain two structures differently of the same or different bacteria, right? Okay, so what are the differential stains? We have three differential stain, and we're going to start with the first one, which is known as the gram staining. So gram staining differentiates between what? It differentiates between what? It differentiates between a gram positive and a gram negative organism. So what is it differentiating between? A gram positive and a gram negative organism, right? So this is what it differentiates between. Who invented this gram staining? There was a scientist known as Hans Christian Gram, who gave us this concept of gram staining, right? And on his name only, we have this gram staining. So now what are the steps going to be? The first step is always going to be fixation. And whenever we are doing this, chemical fixation takes a lot of time. So if we, mostly for gram staining and all, just because we don't want to see the internal structures, we just want to see the morphology, just the shape of the bacteria, that much is enough for us. So we can do the heat fixation also, right? So we can do the heat fixation also. Coming to the steps are CAS, right? CAS. So what does C stand for? The first step is the C. C stands for what? It is a primary stain, which is your crystal violet. So it is obviously going to be violet in color. So this is your primary stain, which is your crystal violet. So everything is going to turn violet. Doesn't matter what shape, what orientation, doesn't matter. It's going to stain everything violet, right? Then next, what is going to happen? Then next is an I. I is what? I is your iodine. And iodine is what? It is your mordant. So mordant actually helps the primary stain to go inside the bacteria. So mordant is kind of helping it to go inside the bacteria, right? And it kind of makes a bond with the primary stain and it doesn't let the primary stain escape out. So that is the function of a mordant. So that is your iodine here. Coming to A. A is what? A is your acetone. So A is your acetone, right? Or your ethyl alcohol. So it is working as what? It is working as a decolorizer. That means that some bacteria are going to lose this primary stain because of this decolorizer, right? Some are going to retain this stain and some are going to leave that stain. And with the help of a decolorizer, the other bacteria are going to lose their stain. Now we do want to see the shape of these other bacteria also. So what do? We put a counter stain or a secondary stain, and they are the safranin. So it is a secondary or we call it as a counter stain. So whatever is left, that is going to be stained by safranin. So your crystal violet, as the name is suggesting, is going to be violet in color and your safranin is pink in color, right? It's going to be pink in color. So let's see here. So this is what I have made. This is my smear. It is a heat fixed smear, which is fixed. Next, what am I going to do? What have I added? Here I've added the primary stain, which is my crystal violet. Hence, all the organisms have become violet here. So everything is going to be violet here. Then what have I done? I have added a mordant here, which is what? Which is my iodine, right? So it has kind of fixed it more. So this has been added. Next, what is happening is now here I have added a decolorizer. So what is happening is that some organisms have lost their color. Can you see this has lost its color? But now I do want to stain this. So what am I going to add? I'm going to add a secondary stain, which was my safranin. So all these organisms took up that stain and became pink, right? And they became pink. So these are the steps. Now what organisms take up the primary stain and what organisms take the secondary stain? Let's see that. So all your gram negative organisms, most of your gram negative organisms are going to take up the counter stain and they're going to lose the primary stain and become pink, right? And become pink. Versus all your gram positive organisms are going to what? Are going to be violet in color. So gram positive, when I say, I talk about the crystal violet, and when I say gram negative, I talk about the safranin state, right? So why is there a difference in this? Why is there a difference? Because there is a difference in the cell wall. So all the gram-positive organisms, what are the cell wall? It has a very, very thick peptidoglycan layer. So when you have a very thick peptidoglycan layer, what is happening is that when the primary stain is entering inside this peptidoglycan layer and the mordant is entering, it is making a very strong bond. And because the peptidoglycan is so thick on it, that when we are putting a decolorizer, it is not, that stain is not going out because of that thick peptidoglycan layer, right? So that primary stain is not able to escape. Versus what is happening in a gram-negative cell wall. Can you see the peptidoglycan is so thin? The cell wall is so thin that what is happening here is that it is able to release that primary stain very easily. Right, even if the iodine has made a bond, that whole layer, the peptidoglycan layer, is so thin in your gram-negative cell wall that it is going to actually let the primary stain be released. So when the decolorizer is added, the primary stain is going to get released and they're again going to become unstained structures. That is why when I'm putting a counter stain, which is my safranin, these gram-negative organisms are taking that counter stain and becoming pink. So the whole thing based upon the differentials of gram positive and gram negative are dependent on what? Are dependent on your cell wall, which is the peptidoglycan cell wall, right? So that is your basic principle. So now I want you to remember one thing, that you do get a lot of questions on what organisms are gram positive, what organisms are gram negative. So I've made it easy for you. So you just have to remember that all cocci are the ones that are the round structures, that are the grape-like structures. So all cocci are gram positive. Except what? Except three. And those are the N, M, and V. And what are those? N is for your what? N is for your Neisseria. So N is for your Neisseria. I'm going to zoom it in for you. So N is for your Neisseria. Then what is M? M is for your Moraxella. And V is for your Vionella. Right? So these three are actually gram negative. These are actually gram positive bacilli. So these are what? These are your gram negative cocci. Right? So these are your gram negative cocci. Right? So these are your, only these three are your gram negative cocci. Rest all the cocci are going to be what? It's going to be gram positive. Coming to what are gram negative bacilli? So all bacilli are gram negative. All bacilli are gram negative except the McDonald. So that means these ones, these ones here are what? These are the gram positive bacilli. So all these are gram positive bacilli. So most bacilli are gram negative, but these ones, these McDonald ones are your gram positive bacilli. So let's see what are those. So for M, you have your mycobacteria. So you have mycobacteria. Then A, you have your anthracis bacilli. Then C, you have your clostridium. You have clostridium. Then with D, you have diphtheria. Then O is going to be combined with the N and it's going to be for nocardia. Then A is for what? A is for your actinomycetes. It is for actinomycetes. Then from L, you have the listeria. And finally, with the D, you have the diphtheroids. Right? You have the diphtheroids. So these all organisms are actually gram-positive bacilli. Other than these, all the other ones are your gram-negative bacilli. Right? Got it? Okay, so that was all about the gram staining. Now we're going to come to another staining, which is your acid-fast staining. So acid-fast staining means that these organisms have something in their cell wall that they are able to resist the decolorization by acid. So they have what? They have mycolic acids in their cell wall, because of which if I am putting an acid on them, they are going to resist decolorization. So they resist decolorization by acid, right? So let's see what are the different acid-fast organisms. So we can divide them into bacteria, parasites, and others. So what all organisms come under it? Let's see. So with the bacteria, we have the mnemonic element, right? So with L, you have what? You have your leprae, which is your Mycobacterium leprae. Then you have your Legionella, Mycardidi, right? Then with M, you have your Mycobacterium tuberculosis. Then with N, you have what? You have your nocardia. So these are the four bacteria that are acid fast. Coming to parasites. So you have three parasites here, which is your Cryptosporidium, which is your Cystoisospora and your Cyclospora. And all these three are known as what? They are called as coccidian parasites, right? So they are called as coccidian parasites. Other than that, you have two more, which is your Microspora, and E stands for eggs. And whose eggs? There are two parasites whose eggs show this, and one is what? One is your Schistosoma mannsoni. So Schistosoma mannsoni eggs are acid fast, and your saginata. What is your saginata? There is your Taenia saginata eggs are your acid fast. Coming to others, what others? So there are two S. One is your sperm head. So the head of sperm is actually acid fast, and your spores are acid fast, right? So here only I want you to know that what is the percentage of your acid fastness that they can resist. So what is the acid that we use here most commonly? The acid we use here is the sulfuric acid, which is your H2SO4. So there are different concentrations of sulfuric acid based on what we call it as a modified Zn stain. So we are modifying the concentration of the sulfuric acid. So based on which they are basically resisting the acid. So the more amount of mycolic acid an organism is going to have, the more percentage of sulfuric acid it can resist. Right, so let's come to the first, which is what? Your lepra and legionella. So your lepra bacilli can resist up to 5% of sulfuric acid, whereas your legionella can actually resist 0.5 to 1%, which means that there are very, very few mycolic acid in the cell wall of Legionella mycardida. That is why it's only able to resist 0.5 to 1% of sulfuric acid in comparison to the lepra bacilli. Coming to TB, TB actually can resist 25%, which means there are a lot of mycolic acids in the cell wall. So higher concentration of acid can be resisted. Coming to nocardia also shows 1%, right? Easy way to remember parasites. All parasites show what? All parasites show 1% resistant to acid, right? Other than that, the sperm head shows 0.5 to 1%, and your spores also show 0.5% resistance, right? So these are all the organisms that show your acid fastness. And then we have the bacteria, parasites, and others, and the different concentrations at which they can resist the acid. Right? Coming to the steps. So in steps, first is always going to be the heat fixation. We've already spoken about it. And now I wanted to tell you that there are two methods that by which we can do this form of staining. And what is that? It is the Zn, which is also known as the Ziehl-Neelsen staining, right? And then there is the Quignon stain, right? So one more thing I want you to remember here is that the Zn stain is also called as a hot stain because we are heating here. So we are heating the slide here. That is why it is known as a hot stain. And in Quignons, it is known as cold staining because we are not doing any kind of heating, but we are modifying the stains in a way that we don't require the heating, right? So let's see what is the primary stain. So what is the primary stain going to be? The primary stain here is going to be your carbon fission. So it is going to be your carbon fission, right? So in both the places, it is going to be what? It is going to be carbon fission here also in the cold staining. But what is happening here is that the concentration of the carbon fission is increased. So that is the first modification. In Quignons, you increase the concentration of carbon fission, versus in your ZN staining, you use the simple carbon fission, right? And this is what color? This is pink in color. So all bacilli are going to take this carbon fission. Next, you do what? In your ZN staining, one thing that you do here is you're going to heat. So you're going to heat, which is something that is absent in your quinones. You're not going to heat. That is why it is known as a cold staining, right? Coming to the decolorizers. Decolorizer is going to be what? It is going to be sulfuric acid, right? It is going to be your sulfuric acid in your ZN staining. But what is it in your quinone? So this is the modification where you're using acid alcohol. So because of this acid alcohol is the reason why you don't require this heating. Right. So this acid alcohol is only going to make the pores on the cell wall and you don't require the heating. Coming to the secondary stain now. So after that decolorization has happened, what is going to be my secondary stain? My secondary stain is going to be methylene blue, right? My secondary stain is going to be methylene blue. So it is going to be stained methylene blue in both of them, in your ZN also and in your quinones also, right? So that is your different steps for your cold staining and your hot staining. And what are you going to see now? So these are what you see. So you will see the pink colored bacilli against a blue background. So what will you see? You will see the pink colored acid fast bacilli against a blue background. So these are the pink bacilli against blue background, right? So that is what you are going to see here, right? So what is it differentiating between? It is differentiating between acid fast positive and non-acid fast organisms. So what is it differentiating between? Acid fast and non-acid fast organisms, right? Understood? So acid fast and non-acid fast. So now the next stain that we are going to be talking about, which is another differential stain, is going to be the Albert stain. And what do we do the Albert stain for? We mainly do the Albert stain for one species of bacteria, which is known as the Corynebacterium diphtheriae, which causes what? Which causes your diphtheria. So diphtheria particularly has what kind of a pattern? It has the Chinese pattern appearance. And can you see this picture here? So these are the different kind of Chinese pattern appearances that the diphtheria shows, right? So diphtheria produces one kind of granules which are known as the metachromatic granules or the volutin granules or the Babes-Earns granules. So these granules are actually the powerhouse of the diphtheria and they store the energy. So when it comes to the differential stain, what is this Albert stain doing? It is actually differentiating between the diphtheria that can produce these metachromatic granules and the other form, which are the diphtheroids, which look very, very similar to diphtheria, but they don't produce these metachromatic granules. So this Albert stain actually stains these metachromatic granules, and that is how they are able to differentiate. So diphtheria is actually a gram-positive bacilli. Remember that mnemonic McDonald's? So they are producing the gram-positive they are the gram-positive organism producing these metachromatic granules, and that is the differential stain here, right? So what are the steps now? So the first step is always going to be the heat fixation, right? So it's always going to be the heat fixation like all the other ones. And now we have what stain? So the first stain that we have is your Albert 1, right? So we have the Albert 1 and what all? So this is a primary stain and what all does it contain? It contains your toluidine blue, right? It contains your toluidine blue and contains your malachite green. So it contains your toluidine blue and malachite green. Other than that, it has what? It has your glacial acetic acid and it has alcohol. So all of these are the constituents of your Albert 1. So once you've stained the slide with Albert 1, this is usually done for what? For 5 minutes. You wash the slide and then you put an Albert 2. Albert 2 contains what? It contains iodine and your potassium iodide, and this you leave for 2 minutes. Right, so iodine is again you're acting as what? Acting as a mordant. So your Albert 1 contains both your primary and the other stain, which is your toluidine blue and malachite green. Then it has glacial acetic acid and alcohol, right? Then you wash it and then you put an Albert 2, which contains your iodine, which is kept for 2 minutes. So what are you going to see? You're going to see a structure like this. So the one on the left is by a gram staining. And what are you seeing? So gram stain were able to tell us if it is a gram positive or a gram negative organism, right? So can you see these? So what are these structures? These are the gram positive bacilli. So our diphtheria is a gram positive bacilli versus what are you seeing in the Albert stain? Now can you see? So in Albert stain what happens is that your bacilli is stained green. So the bacilli is green and your metachromatic granules. So metachromatic granules are what? These ones. So these are what? These are blue. Right, so they are bluish, blackish colored metachromatic granules, and these are only seen in what? They're only seen in your Corynebacterium diphtheriae, and they are not seen in your diphtheroids, which also resemble diphtheria, but they don't contain the metachromatic granules. Right, so that is your Albert stain. Now coming to another stain, which is your bipolar staining. So bipolar in its name only it is suggesting bi means two, right? So bi means two and pole means pole. Polar means poles. So that means that this stain is going to stain the poles of the organism. So it's going to stain the poles and it's going to look like something like this. And what is this? It looks like a safety pin appearance. So it is going to give a safety pin appearance, right? So this is going to look like a safety pin. Now, what all organisms show this kind of a safety pin appearance? Look here also. So they are staining the poles and looking like a safety pin appearance. So what organism? So we have a mnemonic which is can produce very high yield. So can produce very high yield. What is the first organism? It is your Campylobacter. Campylobacter granulomatis. So Campylobacter granulomatis is the one that is the first organism that shows the safety pin appearance. Then from P, we have what? We have your Pseudomallei. And what Pseudomallei? It is the Burkholderia Pseudomallei, right? Then with V, we have what? We have the Vibrio parahemolyticus. Not the cholera, it is the parahemolyticus. Then with H, we have the Haemophilus ducreyi. And finally with Y, we have the Yersinia pestis. So these are all the organisms that show the safety pin appearance. Starting again, can produce very high yield. So we have Campylobacter granulomatis, we have Pseudomallei burkholderia, we have Vibrio parahemolyticus, we have the Haemophilus ducreyi, and finally the Yersinia pestis. So you can get an MCQ on any of these, that what all organisms show safety pin appearance. These are all the organisms that are showing the safety pin appearance. Right, so that kind of brings us to the end of this session. So stay tuned for more sessions on general microbiology.